Good afternoon, folks. Today I'm working out a problem that involves two ropes that are connected to a steel cable that supports a hanging weight, and I've drawn that all in this picture down near the bottom. And the problem asks us to, in part A, draw the free body diagram showing all the forces that are acting on the knot that connect the two ropes to the steel cable. I'll kind of draw that here as a big black dot. We want to show all the forces that are acting on that knot represented by the black dot here. And part A wants us to determine which of the two ropes will have the greater tension based on the force diagram that we draw. And for part B, if the maximum tension that either rope can sustain without breaking is 5,000 newtons, we need to determine the maximum value of the hanging weight that these ropes can safely support. And thankfully we can ignore the weight of the ropes and the steel cable, so that makes everything pretty straightforward. Let's start with part A, where we draw the free body diagram. So with any free body diagram, I always tend to draw a XY coordinate system with plus X moving in the right direction and plus Y moving in the upwards direction. And let's think about the different forces that are acting on the knot. We know that the knot has to support the weight of this hanging mass. So let's go ahead and draw a weight vector that points directly downward. And I'll do that in this purple color here. Okay? And that's W or mg, however you would like to write that. We know that because the angles are different for these two ropes, they are very likely going to have different tensions. So let's label them as perhaps T1 here, and the other one will be T2 there. So if we wanted to express T1 and T2 in our free body diagram, we would draw them pretty similarly to how they would be shown in the picture that I've drawn. The tension will be pointing towards the ceiling. It's not towards the origin. Same thing when it comes to T2. That one will be pointing in this direction, and I'll even label them T2 and T1. And I think this is where some people run into some trouble when it comes to labeling the angles. Before we even go that far, I'm going to make a very quick simplification so I don't have to write 60 degrees and 40 degrees all the time. So let's let alpha be equal to 60 degrees and beta be equal to 40 degrees. And with that said, the question is, how do we want to represent that in our free body diagram? So normally, I think many people would place, let's see, this would be alpha here, and they would place beta right here. And while that is true, that makes breaking things into components a little bit more difficult for students who are not familiar with how that might work. You know, normally students are used to seeing angles like right here or right here. So in fact, what I'm going to do is I'm going to show you how we can take these angles and move them right there and right there. And the trick comes from a property in geometry involving parallel lines. Because notice, I've drawn this really poorly, but the x-axis is a completely straight line, right? So if I wanted to be honest about it, I would use a completely straight, thick line here. And we know that the ropes are connected to the ceiling at the exact same point. So there must be a line here, as I've drawn with this dotted line, where the two vectors would touch. So we have two parallel lines here, the x-axis and where the two vectors touch at the arrowheads here. So I talked about a property in geometry that lets us move angles around. Let me use T1 as an example here. If you have a pair of parallel lines and you draw a line across them like this, similar to the way that I've drawn the vector for T1. If I put alpha right here, oh, oops, I'm still in line. Let me use brushes. Here we go. If I put alpha right here, there is a geometrical property that says that this angle, alpha, right here, is the same as this angle right here. They're both alpha, right? This is what's known as interior alternate. I'm going to put ALT dot interior alternate angles. Okay, so this tells us that I can take alpha and I can put it downstairs to where this red arrow is pointing, to where we might normally find where an angle is located relative to where we draw a vector. Same thing when it comes to beta. It doesn't matter whether I have a line that's slanted this way or I have a line that is slanted, if I do the same thickness, this way. Okay? It doesn't matter. In fact, for the sake of completion even, I will draw where beta would be located, which would be right here. Oops, that's a little big, sorry. Right here is beta. Okay? So the interior, or the interior alternate angle for angle beta would be this one, right here. So I'm going to move beta down right there. So this is the, I think, correct way of representing our free body diagram. And I'm going to remove some of the extra info here because it's drawing a lot of clutter. I want to make it pretty obvious what the final answer is for the free body diagram. So with all this extra stuff removed, our free body diagram is essentially this right here. Okay? We've got our weight vector pointing downward. We've got our T1 vector pointing in the direction towards the ceiling with the angle moved down into the proper location. And the same thing with the T2 vector pointing towards the ceiling and angle beta moved in the proper location. So that is this part of the free body diagram. So now what we have to do is, based on our force diagram that we've drawn for part A, which of the two ropes will have greater tension? Now, we don't know what T1 and T2 are, so understandably that can cause a little confusion. But the trick is to use Newton's second law to determine which one might be bigger. And here's what I mean by that. Let's use the familiar sum of forces equals ma. And what I'm going to do is I'm going to look at this in the horizontal direction. Okay, so essentially this would be the proper equation that we would be utilizing here. So what are the forces in the x direction? Well, if I draw them in light blue for T2, for the positive direction, I have this leg of the triangle that points in the plus x direction, which would be T2 cosine of beta. And similarly, but in the opposite direction, if I draw with this very light green color, sorry, I'm writing over the angle name there, right here, there we go. Here we have T1 cosine of alpha, but because it's pointing in the negative x direction, right, it's negative. So you can either leave the negative here, or you can choose to not write it and just know that it's negative. Either way is fine. It's up to you. But one other thing that we need to consider is that there is a 0 net acceleration in the xward direction. The knot is just holding this mass still. It's not moving left or right at all. So let's do the sum of forces, and then this will be essentially equal to 0 because there's no net acceleration in the x direction. So we have T2 cosine of beta minus T1 cosine of alpha. That is equal to 0. So we can move this piece over, which will tell us that T2 cosine of beta is equal to T1 cosine of alpha. Okay, that's cool. We're getting somewhere. We can divide both sides by T2, and this will tell us, in fact, we'll also both, man, I can't talk. We'll divide both sides by cosine of alpha, as well, times cosine of alpha, which will get rid of this piece. Okay, getting ahead of myself, sorry about that. Which means we have cosine of beta divided by cosine of alpha is equal to T1 divided by T2. Some people will look at the sine component of the tensions and conclude that, you know, hey, since sine of 60 is greater than sine of 40, then T1 should be greater than T2. I don't think that's an extremely strong statement, given that that is a statement that uses trigonometry and doesn't use the tools that have been given to us in this chapter where we're using Newton's laws. But I think that's a good place to start. I think that is that's proper reasoning. So given that type of thought, T1 should be greater than T2. So if we look at this fraction and we actually approach the analysis using the proper tools, then this fraction here, T1 divided by T2, that should be greater than 1. In fact, let me rewrite this. Because beta is 40 degrees and alpha is 60. If I take cosine of 40 divided by cosine of 60, what do I get? Well, it's about, if I approximate here, 1.532. So now I think we can conclusively say that based on the force diagram, using Newton's second law, the proper approach, and, you know, with a little bit of background reasoning from trig to give us a good first approximation to the answer, we can properly say that T1 is greater than T2, right? So T1 is bigger. T1 is bigger, right? So that's it for part A, right? We know that T1 is definitely bigger because it's bigger by a factor of a little bit over than 1.5, so it has to be bigger. With that, let's move on to part B. And in fact, I'm running out of room, so let's copy and paste this part over to a fresh page, perhaps with the picture here too. So if the maximum tension that either rope can sustain without breaking is 5,000 newtons determine the maximum value that the hanging weight can support. We know that since the max tension in either rope is 5,000 newtons, right? One of the ropes has to have a maximum tension of 5,000. Well, it's got to be the case that it's T1. And I say that because T1 has the bigger tension. And we know that 5,000 is the biggest that the tension can be without breaking. So if we chose T2 to be 5,000, that means T1 is even bigger than 5,000. So now you've chosen a situation where the maximum tension is exceeded, and that causes problems. So T1, let me even write that. T1 has to, man, I just can't write today. I'm so sorry. Has to be bigger. T1 has to be bigger. Has to be. For the reason I just said. If you pick T2 to be 5,000, T1 is going to be bigger than 5,000, and you can't have that situation. So here, T1 is equal to that 5,000 Newton number that was mentioned. So with this given, we need to figure out what T2 is, and then we can use that to figure out what the maximum value of the weight that we can sustain is. So let's jump back real quick to the first thing here where we said T1 divided by T2 is this 1.532. Right? I'm going to rewrite this here. So very important info. T1 divided by T2 is approximately equal to 1.532. Well, that tells me that if I plug in 5,000 for T1 right up here, I can multiply both sides of this expression by T2 and then divide by 1.532. And now I've got what T2 is. So here's what I mean by that. So T1, we're going to call this equal, just for really fast purposes here, is equal to T2. And then I would divide both sides by 1.532 just to show all the steps here. 32. This would cancel out. So now I've got 5,000 newtons with an extra zero. There we go. Divided by 1.532. That, according to my calculator, is 3,263.5 about newtons. That's what T2 is. So we have T1 and we have T2. What we can do is we can say that if we take the sum of forces in the y direction, again, we know that the net acceleration is going to be 0 on the knot in the y direction because it's just sitting there. F of y is equal to 0. What are the forces, right? If we go back to our free body diagram, the up-down for T1 would be T1 sine alpha. I'll even draw that right here. T1 sine alpha, that kind of finishes off that leg of the triangle. T1 sine alpha. And then over here on the other side, we've got T2 sine beta, finishing off that leg of the triangle. So the sum of forces in the positive direction are T1 sine alpha and T2 sine beta. And then the negative force would be the weight. So if we plug that back in here, we said, T1 sine alpha plus T2 sine beta minus W is equal to 0. Find the maximum value of the hanging weight that these can safely support. Well, the maximum is going to be this value right here. So let's move W over to the other side, and that will literally tell us, hey, the maximum weight that you can sustain using these tensions and the provided angles alpha and beta as the way that we've defined them, that's the weight. That's the weight that you can sustain. So let's plug in the numbers that we were given. Do not approximate anything up through this point. Save the approximation for when we get to the final answer. So it's totally okay to hang on to this number that has like an extra half on it. No big deal. We'll worry about this in the end. So what is T1 here? We said T1 was 5,000 newtons, and that's being multiplied by the sine of alpha is equal to 60 degrees. Yes. And then we're adding 3,263.5 newtons multiplied by the sine of 40 degrees. We're summing those together, and that's the maximum weight that those ropes can sustain. And when I plug this into my calculator, I get the following 6,427.9 newtons. Here is where we should worry about approximating and consider significant figures, because this is the answer to part B right here. It's a little difficult to determine why we were given one significant figure here, as well as one here and one here, and the answer key wants us to report to 2. I think that a mistake was made in the problem description. Perhaps they meant to say 5,000.0 and then maybe 60.0 and 40.0, because we're supposed to be approximating this to 2 significant figures. So I know that's very confusing based off the rules that we've done before, but you know, sometimes you just kind of have to do it the way that the answer key wants you to do it, based off of how the author is thinking. So let's approximate this to 2 significant figures based off how the answer key wants us to do it. If we made the cutoff right here, we see that 2 is less than 5, so we're going to be approximating to 6,400 newtons in this case. And that is the answer to part B. Thank you for watching.